This lesson is about colligative properties, and the essential question is, how are boiling point and freezing point affected by colligative properties? You'll know you can answer the essential question if, first of all, you can define what a colligative property is, and then if you can explain what happens to particle behavior during boiling and freezing, and then explain why adding a solute to a solution changes the boiling point and the freezing point. Let's start with the definition. Colligative properties are defined as properties of solutions that depend on the number of particles that are dissolved in a volume of solvent, which is basically concentration, and not on the mass or identity of the particles. There are three types of colligative properties. One is called boiling point elevation. Another one is called freezing point depression, or sometimes it's called freezing point lowering. And the third one is called vapor pressure lowering. We're going to focus on boiling and freezing point. To understand what happens when we add a solute to the boiling point of a solution, we first need to understand what's happening to the particles. When we talked about gases, we talked about the fact that as the particles speed up, they get farther apart. Well, the same thing happens in a liquid. As the particles in a liquid start to speed up, in other words, we increase the kinetic energy, maybe by adding heat, they start to spread out. And as they spread out, some of the particles have absorbed enough kinetic energy that they can start to break away from the liquid phase or overcome the forces of attraction between these liquid particles and go into the gas phase. At the same time, though, we've got this pesky thing called atmospheric pressure. So the particles of air are being pulled toward the surface of the liquid by gravity. And as they do, they collide with the surface, and that collision creates pressure. Well, if the particles in the liquid haven't gained enough kinetic energy to create enough pressure in its collisions with the particles surrounding it, atmospheric pressure will push down and collapse the bubble. So we have a teeny tiny bubble starting here, but then atmospheric pressure collapses it, and the particles get closer together again. This slide shows us what happens when we have enough gas molecules forming to create enough pressure so that atmospheric pressure can no longer crush the bubble, so it retains its shape. If we move to the next picture, we can see what happens when we add a solute, however. So the particles along the edge of the bubble that would be escaping into the gas phase are now blocked by solute particles. So we're back again to fewer particles in the gas phase, and therefore enough atmospheric pressure to collapse the bubble again. Here's an animated version. And again, we've got this interface between the liquid, and this is the inside of the bubble. And we've constantly got particles that are moving into the gas phase. Some of them get close enough again to the liquid that they're drawn back into the liquid. But boiling point is when there's enough gas pressure inside this bubble that atmospheric pressure can't collapse it. Okay, and here I've added some solute particles again at the interface. So these solute particles, even though they're not moving, you can see where they're getting in the way of some of those gas particles being able to escape into the bubble. Okay, so the liquid particles were trying to overcome the forces of attraction. The opposite is happening during freezing point. At freezing point, which is the melting point or freezing point, we have a layer of liquid at the surface here. And these particles are cooling off, and the slower they get, or the less kinetic energy they have, the greater the force of attraction to the ice crystal. So they start to organize and form a new layer of ice. If we take a look at the temperature gradient here, you can see that the air particles are at 16 degrees Celsius, the ice is at -4, and right at the surface where the melting and freezing is taking place, it's 0 degrees Celsius. And as long as there are liquid particles here, that temperature will stay at 0. Okay, if we move over to this one, you can see we've added some solute particles into this layer of liquid at the surface. And what that does is it gets in the way again. It interferes with these water molecules so that they can't organize and become attracted to the other ice crystal molecules. And so instead of staying at 0 degrees here at the surface, because they're not freezing, the water can actually decrease in temperature. And so instead of being 0 degrees at the surface, it's now -2 degrees at the surface. So the solute causes the melting point to become lower. This is kind of a cool image. It's two pieces of ice side by side. Room temperature is about 18.5 degrees Celsius, and salt has been applied to the top of the piece of ice on the left. So as we watch the video, he's going to take the temperature of both pieces of ice, and we can see that the thin layer of water at the surface on the left gets all the way down to about -16 degrees Celsius, whereas the one on the right stays at about -3.5 degrees Celsius. So for boiling point elevation, just to review again, the boiling point of a solution is always higher than the boiling point of the pure solvent. And that's because this solute is interfering with the molecules that are trying to escape into those gas bubbles. Freezing point depression, the freezing point of a solution is always lower than the pure solvent. And the reason for that is because the solute, again, is interfering with these attractive forces. Notice these particles being attracted toward the ice crystal, but they're having a hard time organizing around the solute particles. This also shows us that why it doesn't matter what kind of particles we have as solute, but how many. Because notice if I take one of these away, then these water molecules are able to organize and crystallize. So the more particles you have, the more interference they create, and the more the boiling point elevation or freezing point depression increases. We've got 3 different kinds of particles here. And even though it doesn't matter what kind of particle, it does matter if they're ionic or covalent. Covalent particles like sugar, and here we've got a sugar molecule, one end is slightly positive, one end is slightly negative, so it is attracted to the water molecules and it will dissolve, but it doesn't break down into its individual atoms. It stays in its molecule form. So 1 mole of sugar will produce 1 mole of solute. If we have an ionic compound, however, not only does salt dissolve, but the water molecules also pull the ions away from each other. And so we can see here that a mole of sodium chloride will produce 2 moles of solute particles. So not only will the sodium get in the way, but the chloride will get in the way as well. And then here we've got an example of potassium phosphate, K3PO4. The blue molecule, or the blue ion, is the phosphate, and then the 3 purple ones are the potassiums. And notice that when it dissolves in water, it can actually create 4 particles or 4 moles of solute. So ionic compounds tend to be much more effective at raising boiling point or lowering freezing point. All right, so here's a good example of the colligative properties at work. This is a label of an antifreeze bottle, And normally water freezes at 32 degrees and boils at 212. And we can see that by adding this antifreeze to the radiator, we can actually lower the freezing point dramatically to negative 84 degrees, and we can raise the boiling point all the way up to 276. So the radiator's less likely to boil over and it's less likely to freeze. This next one is adding salt to water. And it's kind of a misconception that adding salt to the water will cause it to boil faster. As a matter of fact, it will actually take longer for it to come to a boil because it's going to boil at a higher temperature. It's going to take more kinetic energy. The advantage of it, besides taste, which is the major advantage, is that because it's boiling at a higher temperature, the food will cook faster. Now it's time for you to reflect on what you've learned. So go ahead and look at the essential question again. How are boiling point and freezing point affected by colligative properties? And make sure you can answer that before you move on to the questions.